So up until this point, we've been talking about limits, and I believe that you've fallen into one of two camps. You've either just accepted everything that I've said about limits and learned how to evaluate limits and just rolled with it. Or you're the type of person that's been asking the question, what really is a limit? And I pulled some sleight of hand, and in reality, I never told you what a limit was. I told you sort of what a limit was, and I told you how to find limits in certain situations. But what is a limit? So up till now, this is what we've said a limit is. If a function, f of x, gets close, and I'm going to put that in quotes, to L, so to some real number L, as x, and here it goes again, gets close to some real number a, then we write this. Limit as x approaches a of f of x equals L. But here's the problem. What do I really mean by gets close? This is a very good intuitive definition, meaning that it's perfectly fine to think this way in your mind. Okay, when you think about a limit, you think about a function value getting close to a number as the input variable gets close to a number. That's really what a limit is. But it is not a precise definition. In mathematics, we want to be extremely precise because we want our arguments to be based on just a handful of axioms and everything to follow using deductive reasoning. This is not a precise statement. It's not based on anything. It's just an idea. It's just an intuition about how we can think about limits. So now I want to tell you the precise definition of a limit. So unfortunately, this is one of those times where I'm going to write something that is going to make everything way more complicated. And again, we're sacrificing intuition here for mathematical precision. I just want to keep that in the back of your mind. So here's the precise limit definition. So the limit is x approaches a of f of x equals L if, here we go, for every small number epsilon greater than 0, so epsilon really can be any real number, but we want to think about as epsilon being arbitrarily small, there exists some positive real number delta such that so for each x in the domain of f, satisfying this. So basically the difference between a and x needs to be less than delta, but also strictly positive. So this is just ruling out the case that we're actually at x equals a. Okay, so every such x that satisfies this, we have the following. The distance between f of x and this number L that we're saying is the limit should be less than this arbitrary small real number epsilon. Okay, so I'll just let you read this and just take it in. Just try to soak it in. So if this is your first time reading this, just know that it's okay if you're a little bit confused. But this is extremely precise. This is as precise as it gets with limits. And the idea here is going to probably be made significantly more clear if we look at a picture. So let's look at a picture. Okay, so here's our picture of our function f of x in blue. And so recall that for the limit, let's write it down, the limit as x approaches a of f of x, I start with this number L in the range of the function, maybe not in the range of the function, but in the y value of L, and I pick some number epsilon. I can pick any number I want. And I would like epsilon to be relatively small, so I can really think about this distance getting really, really small. So I want my function values to land in a really, really small window around L. And if the limit exists, then I should be able to find a window in the domain around A, such that if I take an x value in here and look at the function value, it's going to land in this small window around L. Okay, so it's like if I zoom in as close as I want around this number L, I can find a window that I can zoom in the x direction, or in the domain of the function, for which every x value in there outputs something in this window. Okay, so hopefully that picture starts to give you a feeling for what's going on. And it's a couple of things that are important about this limit definition. So how do we actually use it? So the interesting thing first is that to use this definition, I actually have to have a guess for what the limit is. This definition doesn't tell me how to find the limit. Okay, we've actually already talked about how to find limits using the limit laws, simplifying indeterminate forms, etc. This is actually to prove or justify limits. Once I have a guess that the limit is L, I actually use this to prove it. So you always start with an arbitrary epsilon. I don't get to pick epsilon. Epsilon is just any arbitrary number. That's just giving me the window I'm trying to shoot between. My job to prove this limit is to find delta. And I'll find delta in terms of epsilon. So actually delta will depend on epsilon. The bigger epsilon is, the more wiggle room I have for delta. The smaller epsilon is, the less wiggle room I have for delta. But this is the game. I start with an epsilon. You give me an epsilon. My job to prove the limit is to find this delta that will depend explicitly on epsilon, so it'll be a function of epsilon, such that if you pick something in this window, so this window here is exactly this window right here. It's just a fancy way to say this window right here. And notice that I'm actually excluding A. Okay. such that if we pick something in this window, then what do we have? The distance between f of x, so evaluating the function at that point in L, has to be less than the original epsilon you gave me. Okay, so you give me an epsilon. My job is to find delta in terms of epsilon, such that when x is basically close enough to a, so within delta of a but not equal to a, the function values are all landing within epsilon of this L value. And that proves the limit. So this is really a proof that we need to do. Okay? Because we already know the answer, theoretically. We're going to guess the answer, and then we're going to prove it. Okay? So this is probably one of the first tastes that you get into a mathematical proof. And so if you're tracking, hopefully you're really excited, because the idea of proving something is cool. Because you're not just saying, oh, it's like this, or it's like this because it seems like that should be the way it is. No, this is concrete. This is just coming from the most basic assumptions we can have. This is what a limit is. We can prove that that's what the limit is. So if you're tracking with me so far, you'll remember that we actually had different types of limits. So we had kind of the standard limit that we've already given a precise definition for. But we also had one-sided limits. And then we also had limits that involved infinity. And we can actually give very precise definitions for those as well. So for one-sided limits, things are not so bad. So all we want to do is replace. So remember, we had this window where the absolute value of the distance between x and a was less than delta. We just replaced that with the following condition. So x should be between a and a plus delta. This is for a right-handed limit. Or, so this is like just to the right of a, or a minus delta is less than x less than a for left-handed limits. And you see that if x is between a minus delta and a, it's going to be just on the left half of that window. So that's all well and good. What about infinite limits? So let's look first at what I'm going to call truly infinite limits. And this is limits as x goes to infinity. So the limit as x goes to infinity of f of x is equal to L. So now it doesn't really make sense to find a delta so that x is within delta of infinity. So that doesn't make sense. But what I need to find, so again, I have to be given an arbitrary epsilon greater than 0, so a small window in the range. But this time I want a capital M bigger than 0, such that what? Well, x is going off to infinity. So I want to find an M so that basically all x's after that M, my function values are very close to L. And that's sort of that leveling off process that we saw with infinite limits. So such that for each x bigger than M, we have this, f of x minus L in absolute value is less than epsilon. So if x is large enough, basically, then the function is going to be very, very close to, remember, that horizontal asymptote, in this case y equals L. And of course, I'll just make a note, similar is the case for minus infinity. So similarly for minus infinity, all we need to do is just, instead of finding a large positive number, we just need to find a large negative number, because we're going the other way, and that would be for all x values less than that negative number. So again, this is just giving you a taste into kind of the precision that goes into what's called mathematical analysis, which is really justifying all the things that we're just kind of going over and conceptualizing in calculus. So recall that we also had another type of infinite limit. And that was the case when you actually had a fixed number, but the function was going off to infinity. So instead of x going off to infinity, we actually had the function values going off to infinity. So the limit is x approaches a. So now x is approaching a real number, but the function is going off to infinity if what? Well, things change a little bit different here, because now it doesn't make sense to say the function values are within epsilon of a real number. The function values are supposedly going off to infinity. So here, we need to say if for any positive number m, there is a delta. So again, now x should be within a small distance of a. So if there's a delta greater than 0, such that if x is within delta of a but not equal to a, then f of x, just f of x, should be larger than whatever m I found. So I can just let m get as high as I want, and f is just getting bigger and bigger and bigger as I find those values of x closer and closer to a. So the idea is, it's not so different. I think, to the extent that you understand the original precise definition of the limit, this should follow okay. And then, of course, I'll say, similarly, minus infinity and two-sided. Because, I mean, we've kind of already talked about the case for two-sided limits. You just want to replace this guy with either x being between a minus delta and a, or a and a plus delta. And then for minus infinity, you just want, instead of f of x to be larger than some big positive number, you just want it to be less than a large negative number. All right, so now that I've thoroughly confused you with the precise definition of the limit, let's actually do an example to see how it goes. So remember, the game is this. I start with any positive number, epsilon. And my job is to find delta greater than 0 that will depend on epsilon, such that when I'm within delta of this, in this case 1, My function values are within this epsilon, so whatever epsilon was chosen originally, within 2. So the idea is to work backwards. Okay, so I want this f of x minus 2 in absolute value to be less than epsilon. So let's just write down what that means. So f of x is 5x, so this is what I want. So 5x minus 3, that's f of x, and then minus 2 in absolute value to be less than epsilon. Okay, but let's just simplify this a little bit. So this is 5x minus 5 is less than epsilon. Okay, so if 5x minus 5 in absolute value is less than epsilon, that's the same thing as just saying that 5 times the absolute value of x minus 1 is less than epsilon. So all I did is just factor out a 5. And then if I divide both sides by 5, I see that really the condition that f of x minus 2 in absolute value is less than whatever this number epsilon is the same thing as saying the absolute value of x minus 1 is less than epsilon over 5. So what does that mean? That means if the absolute value of x minus 1 is less than epsilon over 5, I can just work backwards and see that, yeah, f of x is within epsilon of 2. So what that means is I want to let delta equal epsilon over 5. And now I'm done. Remember, that was the game. Epsilon was given. My job was to find delta in terms of epsilon, and hopefully now you see what I mean by that. Delta equals just something involving epsilon. And I see that if, okay, this is delta, so if absolute value of x minus 1 is less than delta, epsilon over 5, then I just work backwards and see, yeah, f of x minus 2 in absolute value is less than epsilon. So I'm done. Okay, so we're playing the same game. We're trying to justify or prove this limit. Now, of course, using the limit laws, this is a walk in the park. I just plug in 2 and I get 3. But that's not the goal here. The goal here is not to get the right answer. The goal is to justify the correct answer. So how do we do that? Remember that epsilon is going to be given. So we're starting with some positive epsilon. And my job is to find delta such that, you know, everything holds. When I'm within delta of, in this case, 2, then f of x is going to be within epsilon of 3. So let's just work backwards, exactly like we did before. Let's just write down what we want to be true. We want, for this epsilon greater than 0, for the absolute value of x squared minus 1, so f of x, minus 3, so the distance between the function and the limit we're trying to prove, we want that distance to be less than epsilon. And let's just start manipulating. So here we have x squared, this will be minus 4, less than epsilon, okay? And, well, you may think, okay, I'm stuck here, but of course, you know, I hope you learn from this example what to do in these situations. Notice that this factors. So this actually factors is x minus 2 times x plus 2. And the nice thing here is that this absolute value of x minus 2 is related to what I want to show is less than delta. And the absolute value of x minus 2 times x plus 2 is really the same thing as absolute value of x minus 2 times the absolute value of x plus 2. So now I'm almost done, right? Because if I can just divide by absolute value of x plus 2, then I have the absolute value of x minus 2 is less than something that involves epsilon. But it also involves x. That's the problem. So whatever x is, actually, absolute value of x minus 2 is less than epsilon over absolute value of x plus 2. And I can't let delta be just this term, because delta can only depend on epsilon. And here it would have to also depend on x. So here's the trick. I'm just going to require that delta be less than 1. And now why can I do this? I'm just saying delta is less than 1. Okay, well here's why I can do that. I'm trying to find a delta greater than 0 that's going to make this work. But it's also true that if I find one delta, any smaller delta is also going to work because I'm just narrowing the window sort of unnecessarily if I go even smaller. So actually here, requiring that delta be less than 1 can only be helping me. Now, the delta might need to be even smaller, but to say delta is less than 1 is really no problem. And so what does that mean? If delta is less than 1, that means that x minus 2 is less than 1 in absolute value. So in other words, x minus 2 is between 1 and negative 1. Okay. Then I'm going to add 4 throughout this inequality. So plus 4, plus 4, plus 4. And why did I do that? Because now I have something about x plus 2. So x plus 2, if delta is less than 1, has to live between 3 and 5. But what does that mean about 1 over absolute value of x plus 2? What this means, if I just flip the inequalities, so I have 1/3. So when I flip inequalities, I have to switch the inequalities over x plus 2 less than 1/5. And these are all positive, so actually I can just put absolute values here. It's not going to make a difference. So I see that 1 over x plus 2 is less than 1/3. So actually, I can just say that epsilon over absolute value of x plus 2, assuming that delta is less than 1, is less than epsilon over 3. And now that's a fixed number. So as long as delta is less than 1, absolute value of x minus 2 is going to be less than, well, whatever number is epsilon here over absolute value of x plus 2, which is less than epsilon over 3. So if I'm working backwards, I want absolute value of x minus 2 to be less than epsilon over 3. So I'm going to let delta equal the minimum between 1 and epsilon over 3. And so why do I need this minimum? Because, well, this inequality, absolute value of x minus 2 less than epsilon over 3, is only true if delta is less than 1. So even if epsilon is 100, I still need delta to be less than 1 for this to be less than epsilon over 3. But now think about the other case. What if epsilon is really, really small? Then delta being less than 1 is not enough. Because like if epsilon is just 1 or a half, then this is going to be smaller than 1. So I don't know if absolute value of x minus 2 is less than epsilon over 3, just knowing that it's less than 1. So what do? I just require that delta be less than 1 and epsilon over 3. So just let it be less than the minimum of both of them. And you can see, working backwards, that this delta really will work. Okay, so here we're actually dealing with an infinite limit. The limit is x goes to infinity. So now remember, now the game is, I'm still starting with an arbitrary epsilon greater than 0. I don't get to pick that. That's given to me. It can be any number greater than 0. My job with the infinite limit is to find a real number m bigger than 0 such that what? Well, my function, in this case, L is 0, so the difference between my function and 0 is less than epsilon when x is bigger than m. Okay, but the strategy is the same. Let me just write down what I want to be true. I want absolute value of 1 over x minus 0 to be less than epsilon. Okay, so let's just flip some things around. This is just 1 over x, an absolute value is less than epsilon. Okay, and so then if I just flip this, I can first of all assume that x is positive, right? Because I can just require m to be a positive number, so the absolute value is no problem. So I have that x, if I flip x, so 1 over x flipped is just x, should be bigger than 1 over epsilon. But then why don't I just let m be 1 over epsilon? So if I let m be 1 over epsilon, then I'm done. Because if m is 1 over epsilon, and x is bigger than m, x is bigger than 1 over epsilon, that'll mean that absolute value of 1 over x is less than epsilon, and that's what I want to show. So here we have another infinite limit. The limit is x goes to 0 from the right of 1 over x. And we want to show that that equals positive infinity. So remember, now the game's a little bit different. Now I'm given some arbitrary large positive number. And my goal is to find delta, which is positive, such that, well, f of x should be bigger than m, whatever that number that was given to me, when, in this case, okay, so the difference between x and 0 should be small, so less than delta. But remember, I'm looking at the limit from the right. So when x is between 0 and delta, and here I'm not using absolute values because I really mean x is a positive number between 0 and delta. So again, let's just write what we want to be true. We want 1 over x to be bigger than this number m. Okay, but now let's just flip the inequality. This is very similar to what we did in the last example. We see that x should be less than 1 over m. But that's great, because now we can just let delta equal 1 over m. And why did we do that? Because if delta is 1 over m, if x, now we're thinking about x being a positive number here, so if x is less than delta, x is less than 1 over m, but that means that 1 over x is greater than m for any m we want. So we're done.